One thing that's supposed to be course evaluations to be done electronically. Has any of you received any communication there? And I was supposed to receive something I didn't, so I probably just for that. So most likely you will get an email with a link for an evaluation. Homeworks, Michael graded them this time. Any questions, points? So most of you noticed that I changed a few of the numbers compared to what is in the book. Some of you just copied the template solutions from wherever you found them without even noticing that they're different numbers, and there were actually no points this time. Final exam. So we have pretty much covered all the textbook material. Final exam will be on the 14th. Right, 9 to 12, right here. I myself will actually not be here. I'll be in Munich, in Germany at the time, so somebody else will come to that. So, what I would like to do today is now show you a little bit how everything that we have covered so far with radiation mechanisms and with relativity, how that actually fits into astrophysics, in particular how it fits into what we do here in the center, especially what I do in my group. Before I do that, are there any questions, anything we should avoid? One thing mentioned, there is another homework set posted, but that is completely voluntary. It's not going to go into the grades, you don't have to submit it. If this is just for you to practice, you kind of see what kind of problems there might be on the last part on the relativistic electrodynamics. If you like to hand it in and have me look at it, of course I will do that, but you don't have to submit it, it's not going to go into the grade, it's just voluntary. Any questions, anything you'd like to discuss, any part of the class that you want to discuss in more detail before I jump into this? If not, good. Then, as I said, sit back, relax, enjoy, as I take you through a little bit of how radiation and relativity fits into astrophysics in general, and especially what we do right here. So, radiation, I mean, most of you probably know that what we see as visible light is only a small part of the electromagnetic spectrum, right? So this is all radiation. So what we have done with radiation theory describes all types of radiations from radio waves through infrared, optical, visual light, ultraviolet, X-rays and gamma rays. The only difference here is really just wavelength. You know, within optical light, we have different wavelengths that we see with our eyes as different colors, right? So short wavelengths or high frequencies is blue light, and long wavelengths is red light. And of course, everybody knows that wavelength lambda times frequency is just the propagation speed. So that means you can convert frequency as essentially inverse of the wavelength. So as we go to long wavelengths, though beyond the red, going to infrared and then to radio, to lower frequencies and to higher frequencies, so shorter wavelengths, we will talk about it, and gamma rays, right? And everybody also remembers that we can describe light in terms of photons and particles, right? With an energy that's h, so the Planck constant times the frequency, right? So as frequency goes up to the left here, that means we have higher photon energies. Now for something to radiate at higher photon energies, the particles that radiate must have higher energy, right? We can express that at least somewhere in this range in terms of temperature. That means if we start here at radio waves, in principle this is something that would correspond to very low temperatures, but actually what we see in radio is not really temperature specific. This is actually other radiation mechanisms that we'll discuss. But the analogy works a little bit if we then go into infrared here. So we have infrared telescopes that actually see infrared radiation from space, that probes anything that has maybe a few hundred degrees Kelvin. Familiar with the Kelvin temperature scale? Right? absolute zero, 0 Kelvin, minus 273 degrees Celsius, right? And things in the universe that are a few hundred degrees warm, that is actually mostly dust. So space is not completely empty, there's gas and dust. And what we see with infrared is mostly dust, where light from stars shines onto dust, warms it up, heats it up a little bit, and then it radiates off. We go to higher temperatures, then we go into the visible light range. Because visible light, that is bodies that are about a few thousand degrees hot, and that is actually mostly stars. Anybody know what the surface temperature of our sun is? Must be a few thousand degrees, right? About 5,700 degrees. So that's the main reason. If we look up in the night sky, most of what we see is stars, because stars have just the right temperature to radiate invisible light. Then go to even shorter wavelengths, higher frequencies, the ultraviolet. Still, most of what we see is actually stars, but the hotter stars, more massive stars than our sun, that are 10 to 100,000 degrees. And then we go to more extreme settings. We observe X-rays. With X-ray satellites, we observe mostly things that are a few thousand degrees, a few million degrees hot. Quite often, for example, that is a black hole that sucks in matter, gas from a companion star that settles into an accretion disk and heats up to millions of degrees. That's actually the brightest kind of X-ray sources that we have in the sky. And then we can go to even more extreme energies, where again the temperature analogy actually breaks down. There aren't really things that are more than 100 million or billion degrees hot. It's actually other mechanisms that make the radiation. We'll talk about that. But, so the most energetic, the most violent processes in the universe, those are the ones that shine in gamma rays, and those are the ones actually that we are interested in my group, in Christoph Fenter's group. If you've heard Yuli's colloquium last week, talked about the supernova remnants. He'll join us for the next academic year, and he'll also work on all kinds of things that with gamma rays. I'll talk much more about all the fun things that we can do with gamma rays. When we observe all of this, I mean, it's nice to talk about it. The question is, can we actually do astronomical observations in all of these wavelength ranges? The big problem here is what is plotted down here in the bottom. Namely, as you go through this electromagnetic spectrum from gamma rays to radio, this shows what our atmosphere actually does to all this radiation. You can see optical light and visual light that reaches down to the ground. That's why you can look at it with your eyes. This is of course the reason why our eyes are sensitive to this regime, because this is the light that can actually penetrate the atmosphere. That's why you can look up in the sky and see visible light from stars. If we had ultraviolet eyes, then everything would look dark, because nothing gets through the atmosphere from space. The same with gamma rays. Infrared has the same problem. There's another window here in the radio. So that's why if you want to do astronomy from the ground, you can only do that with visible light or with radio. Everything else, somehow you have to get past the atmosphere. Usually just satellites. So, because South Africa is a really good place to do astronomy, in particular because, as you probably know, we are building the world's largest research infrastructure ever built by mankind, the square kilometer array. So a radio astronomy array that will spread all across the southern half of Africa, essentially. And a predecessor array, Meerkat, of 64 radio dishes, has actually been inaugurated last year and is now already operational. So that is already the most sensitive radio telescopes that exist. And just about a 2-hour drive, 1.5-hour drive from here, we have a smaller radio observatory, the Hartiger-Stuck Radio Observatory. It's a bit west of Pretoria. And of course we have the largest single optical telescope in the southern hemisphere on the world, in Sutherland, southern South Africa. That's a 11 meter actually, single crystalline telescope. Now, for all other wavelength ranges, we have to do some other tricks, like for example infrared. There's satellite, or the Spitzer Space Telescope is one of several infrared observatories that are orbiting Earth in terms of infrared. Ultraviolet, there's actually very little that observes in ultraviolet. This is a rather old mission that's no longer active. Galaxy Evolution Explorer, that was an ultraviolet satellite. Some other optical support telescopes on satellites also go a little bit into the ultraviolet. And ultraviolet is generally quite tricky to observe. Then we have a number of really good X-ray telescopes up there. For example, the Chandler X-ray Observatory that really produces nice high-resolution images in X-rays. That's up in space since 1999. And the big thing in gamma ray astronomy is the Fermi Gamma Ray Space Telescope that I'll talk a little bit more about. That is in orbit since 2008, observes gamma rays. And what I will especially talk about, we are very much involved in Namibia, about 120 kilometers west of Windhoek, Namibia. We have the world's largest ground-based gamma ray observatory. And probably wondering, if the atmosphere is opaque, how can we observe gamma rays from the ground? I will explain how we do that also later. Okay, so just to bring across the point, what we do with radiation theory, we actually describe radiation across this entire electromagnetic spectrum, and what we describe we can actually measure with some of the best facilities in the world, actually right here in Southern Africa. Okay, probably the most important result from this semester is this statement up here that accelerated charges radiate. If there's one thing you take away from this is it, because we have calculated the electric fields from moving an accelerated point charge, and everybody remembers the term that contributes to radiation is this one here, because it has this additional length scaling, so it decays as 1 over r. Everybody remembers that, right? And that term involves the acceleration term. The definition of U here, and then everybody also remembers that for these kinds of fields, the magnetic field is very simply related to the electric field just by unit vector across electric field. And based on that, the radiative flux, the Poynting flux, so the energy flux in radiation per unit area, E cross B is then simply calculated also as from this electric field, from this acceleration term of the electric field. Good. So now, how does this work in actual physical, astrophysical settings to create the radiation that we see? And you probably guess why I spent quite a bit more time on synchrotron radiation than it's discussed in the textbook, because that is one of the most important processes in astrophysics. Particles spiraling around a magnetic field, and of course circular motion is an accelerated motion. In what direction is the acceleration going? Pure circular motion towards the center, right? So there is an acceleration there. You can look at the geometry here. So let's say here's the magnetic field. Then the particle goes around in the circle here. Then the acceleration points towards the center of the circle. If we're looking at it from here, and this vector u is the unit vector times speed of light minus v. And you all remember relativity. If the particle radiates, it's moving relativistically, then all the radiation essentially goes forward. So if we see it radiating, it must be moving close to the direction towards us, right? So this vector u must also be kind of in the direction towards us, right? So when looking at this, what direction will this electric field point in the end? So the u is pointing in our direction, A is pointing maybe to the board. That means the u cross A will point that way, right? So the U cross A will point parallel to the magnetic field, and then we do R cross this thing, will go kind of out of the board. So if you look from here, we see the electric fields coming out of the board, essentially. It's difficult to draw here. That means we'll see the electric fields perpendicular to the direction of the magnetic field. And that can be used in astrophysics, in radio observations, and optical observations. If you see polarization, that means polarization, that electric and magnetic fields have a preferred direction in which they oscillate in the electromagnetic wave. And if we have synchrotron radiation, then this oscillation, the electric fields will have preferential direction perpendicular to the magnetic field. So this way, if we see polarization in synchrotron radiation, we can actually tell which way the magnetic field is oriented. So this is one of the fundamental ways how we can diagnose structures of magnetic fields in astrophysical sources. Another thing, so in order for this to work, the electrons actually have to have very high energies. They have to be relativistic. We know there's electrons with Lorentz factors. Everybody remembers Lorentz factor. Energy is Lorentz factor gamma times mc squared. Lorentz factors of 10 to the 3, 4, 10 to the 5, even up to 10 to 6 or so. So extremely relativistic particles. And the spectrum of synchrotron radiation that we see, quite often if we have relativistic particles, that is essentially some kind of power law distribution in energy. So the number of electrons is a function of energy. The higher the energy, the less electrons you have. So this power law index P then is directly reflected in the shape of the synchrotron spectrum. So if we measure the spectrum of synchrotron radiation, it tells us directly what the distribution of electrons, the energy distribution of electrons is. Very important diagnostic in astrophysics. And if you go on next year, maybe do the master's lecture on high energy astrophysics, and actually discuss that in quite a bit more detail. The main point is, so almost everything we observe in radio astronomy is synchrotron radiation. So that's why I spent quite a bit of extra time on synchrotron radiation, because pretty much anything that radio telescopes observe is synchrotron radiation. Particular nice things like this, those are my favorites. There's actually a galaxy here. We'll talk about AGN a little bit towards the end of today. There's a galaxy here, a massive black hole that shoots out streams of gas, jets, and they dissipate somewhere thousands or tens of hundreds of thousands of light years, hundreds of kiloparsecs away from the galaxy. The galaxy is actually very small right down here, and these jet structures are actually way larger than the entire galaxy. And what we see here is then the electrons that are shot, accelerated, and in the magnetic fields they radiate synchrotron radiation. Also, so these supernova remnants, the remnants of exploding massive stars, radiate a lot of synchrotron radiation. The gas shoots out, hits the external medium, shocks, accelerate particles. And here, for example, the optical radiation is actually mostly synchrotron radiation. Synchrotron radiation is really fundamental for understanding astrophysics, astrophysical radiation. Okay, there's other radiation mechanisms. For example, if we have some kind of hot gas, we have a proton here, an electron, that's not an atom. But if the gas is ionized, electrons kind of deflected by passing by a proton. That is an accelerated motion because this deflected motion that produces radiation. And then it makes sense that, well, you can radiate different frequencies, different energies, but you cannot possibly radiate more energy than the electron has. So the spectrum of this is called Bremsstrahlung. Anybody know what that means, where that comes from?
I think in English it's breaking radiation.
Yes, right. So that's actually the German word. Bremsen is the German word for breaking. So obviously this is kind of German invention. So it's breaking radiation or deceleration radiation. and the maximum we get out is the typical energy of the electrons. So if the gas has a certain temperature, then the typical energy of the electrons is a proportional constant K times temperature. And so the spectrum of this Bremsstrahlung radiation, it's not very about thick things, has this kind of cutoff here that corresponds to the energy of the electrons, that corresponds to the temperature. So you can do that, actually measure this spectrum. If it's flat like this and then has this exponential cutoff, that way you can effectively measure the temperature of a gas in astrophysics. In particular example, this is X-ray images, I think from this Chandra X-ray observatory that I showed this Chandra satellite, where if you have an optical light image, you would see lots of galaxies here in a cluster of galaxies. What we see here is the gas, dilute, very low density gas that's between these galaxies in the cluster. And from just measuring the spectrum, this cutoff of the Bremsstrahlung spectrum of this thermal gas, we know that the gas that is between these galaxies in the cluster has about 10 million degrees of temperature. Okay, now one other mechanism that we have discussed is complex scattering. Right? One photon, one electron scattering off each other. We had spent quite a bit of time in class deriving with energy and momentum conservation what the energy is of a photon if we are in the electron rest frame. So if the electron is not moving, the electron is just stationary at rest. The photon just bounces off the electron and it's deflected, say by some angle chi. Then the scattered photon that comes out has an energy that is somewhat lower than the incoming photon, right? Because obviously if the electron is at rest, momentum conservation tells us that the electron must pick up some of this momentum and energy. So that we had derived in class. You'll see why also on that I spent a bit more time than the textbook does. You can now see here in the electron rest frame, if this epsilon prime is much less than 1, then this term essentially drops out. The outgoing energy is the same as the incoming energy, which means it's elastic. The photon essentially just bounces back with the same energy in some kind of random direction. Because the energy is so small that the electron really doesn't pick up much momentum, so the electron is at rest before and after, and the photon just bounces off. So that's called the Thomson regime. There's no other regime if the energy is actually much larger than the electron rest mass energy. So this epsilon here is the photon energy in units of the electron rest mass. We're doing that so that we can have similar expressions. So for gamma, see that was the electron energy over NEC squared, and then we have epsilon as the photon energy over NEC squared. So we have some corresponding units of energy for photons and electrons here. So epsilon much larger than 1 means the photon has an energy much larger than 511 keV, that's the electron rest mass energy. Then, well, 1 becomes unimportant, and well, this term and this term are approximately equal, so that means the photon bounces off with a much lower energy. The electron essentially takes all the energy. Okay. For astrophysics purposes, in fact, this Thomson regime is often the much more important one, so the photon just bounces off with the same energy. So this is for electrons at rest, but we know from synchrotron radiation, actually what radiates most is when the electrons have very high energies. So where this Lorentz factor gamma is actually much larger than 1. The electrons are highly relativistic. Okay, let's look at what's coming out of that. So here we start out now with an electron that's not at rest, but it's moving at high speed, at high Lorentz factor, almost with the speed of light, and it bounces off some photon. So electron goes out somewhere and the photon is scattered to some energy. Alright, so we don't know what that gives us, but we know what happens in the electron rest frame, right? But to go in the electron rest frame, you see why I spent quite a bit of time on these Lorentz transformations and Doppler boosts and relativistic aberration and so on. The electron actually will see this photon under relativistic aberration essentially coming from the front and boosted in energy by this factor. You remember this factor, that's the inverse of this Doppler boosting factor, this Doppler factor. So if the angles of collision are somewhat average random, then on average the electron will actually see this photon coming at a factor gamma higher energy. So it gets a Doppler boost into the electron rest frame. Okay, now we're sitting in the rest frame, and this frame the electron is at rest. We know how that works. If we're in the Thomson regime, so if this energy is still much less than 1, so the photon energy is still much less than electron rest mass energy in the electron rest frame, then it bounces off in some random direction with exactly the same energy. So that means in the electron rest frame, this electron, this photon will bounce off in some random direction with exactly the same energy. Now, we've done that. Now all we need to do is boost that into this frame. But what happens then? The photons are kind of going in all the random directions. But now we are in the frame of a relativistically moving electron, where the photons going mostly. Are they still going equally in all directions, or where would they be going? Yeah, that's the right moving portion, yes. So they will be boosted at sort of relativistic aberration, because most of them kind of in the forward direction. That's why I've drawn it this way. The photons will essentially all go almost in the direction of motion of the electron. What happens to the energy of the photon? They're coming out of this moving electron frame into a stationary frame, and the photon goes forward. What happens to the energy of the photon? What photon energy do you see if I come at you at almost the speed of light and I send a photon towards you? What happens to the photon energy?
The wavelength becomes energy increases.
It increases, right? Another, on average, a Lorentz factor. So if I come at you with a Lorentz factor of 1,000, you see a photon energy of 1,000 times higher, just from this Lorentz boost. So this relativistic aberration and Lorentz boost, Doppler boost, that's again why we spent quite a bit of time deriving all these relativistic aberration and Doppler boost identities. So that comes another factor gamma. We already have a factor gamma in here. So the scattered photon energy that we measure in this frame is actually factor gamma squared higher than the original photon. That's a fundamental thing about quantum scattering on these relativistic electrons, that every time a relativistic photon scatters, the electron scatters a photon, it boosts this up by a factor of gamma squared. So that summarizes that. Electron with Lorentz factor gamma scatters the low energy photon, it boosts it up by gamma squared. So if we take an example, say optical photons, visible light photons have about an energy of an electron volt. Everybody's familiar with the energy unit electron volt. Can somebody define what an electron volt is?
I think it's if an electron moves to a potential 1 volt amount of energy that it obtains, I think.
Exactly. An electron that moves through one voltage of 1 volt picks up an energy of 1 electron volt, and so 1 electron volt is, you know, what that is in more conventional energy of joules.
1.6 think multiply by 10 to the power minus 19.
Very good, yes, 10 to the minus 19 joules. Yeah? Or, let's see, 10 to the minus 12. That's an energy unit in CGS unit that we often use in astrophysics. So that's with a very small energy unit. That's why we don't see visible light actually as individual packages, because the light we see has so many gazillions of photons that you don't pick out any individual photon. But, so, visible light photon, let's say we have a relativistic electron with a Bremsstrahlung spectrum of 10,000. We know there are electrons with even much higher energy than that, so this is not something unusual. What happens to the photon when it gets scattered? It picks up a factor down squared, it's 2 to the 8, 100 million. So the scattered photon from visible light suddenly comes out at 100 mega-electron volt. And that's smack way in the X-ray regime, and then in the gamma ray regime. So I'm spending so much time on this, because this is actually the process scattering photons by relativistic electrons that makes most of the gamma rays that we see in the sky. Probably the most important gamma ray production mechanisms in the universe. So, and as I said, what we do in my group, in Christos, in Yuri's group, that actually all deals with things that make gamma rays. We try to understand how nature does that, especially how nature produces these high energy electrons that can make the gamma rays. So gamma rays are defined at actually more than 50 or 100 keV, and there's no limit to the energy that they can have. So how do we observe these? We had said earlier, the atmosphere is opaque to gamma rays and X-rays and ultraviolet and infrared. So the first thing you can think of is a satellite. So on June 11th, 2008, the biggest thing in satellite gamma ray observatories has been launched, the Fermi Gamma Ray Space Telescope. So that's a telescope that is actually a very wide view of the sky, some 2 steradian, and constantly scans the whole sky, day and night, in a 90-minute orbit. So of course you can't observe the whole sky at a time, so it goes around one half of the sky, and moves down to the south, scans, and so on. So 90 minutes for the north, 90 minutes for the south. So every 3 hours it scans every point of the sky all the time. This is what it looks like, and not exactly how you imagine a telescope, is it? But it actually is a telescope. Of course, it doesn't work like an optical telescope that focuses light and makes an image. The way this observes gamma rays is that gamma rays come into this detector here. These gamma rays have so much energy that they interact and make an electron-positron pair. And it's easy to track electrons and positrons. So photons come in, convert themselves into electrons, positrons, those we can track. In the end, there's a calorimeter that measures the total energy in the electron-positron, because that energy is the energy of the photon. And see, these photons was tracked back to where the photon, electron-positron traced back to where the the photon came from. Right? So we can figure out where the photon came from, we can measure its energy. That's what you want to do with the telescope. So this actually images gamma rays from the sky and tells us the energy of every gamma ray that slams in the air. It's converted, makes an electron-positron pair. So that's how these funny towers there are actually a telescope. And post up and give the